Our final presentation is for the Technology Innovation Award, and there's two co-winners this year, Doctors Kristine Kieswetter and Deepak Kilpadi. Dr. Kieswetter, God, I'm sorry for I'm screwing up your name, is a senior director in the Device Sciences Center of Excellence at KCI, which is a Acelity company, and Dr. Kilpadi is the medical science liaison at Acelity. These two doctors have both been driving forces behind the evolution of the use of negative pressure wound therapy, which has set the standard for advanced wound care. Their leadership has helped amass more published clinical evidence than any other negative pressure wound therapy product on the market, and KCI's VAC theory has been selected for more than 10 million wounds worldwide in recent years. So I'd like to ask them to come up here, and I'm particularly interested in this because in my extended family, we've recently had a wound, and I understand how debilitating these wounds can eventually become. Thank you.
Very much appreciate it. Let's see, moving forward. So thank you very much for the opportunity to speak with you about, actually, can you hear me? Great. Thank you for the opportunity to speak to you about wounds, incisions, and negative pressure. We really appreciate this honor. Just as full disclosure, we are employees of KCI and now 3M, and the products that we're going to be talking to you about require prescription, and so they require training for clinicians who are going to utilize those products. Dr. Kowalski asked a little while ago, what's the next big thing? I would propose it's wound care. Depending on your source, between 6 to 10 million people a year in the US have chronic wounds. To the cost, again, depending on your source, between $30 to $80 billion a year that we are putting into getting wounds taken care of in the US. You can see that there's a wide range of etiologies with respect to kind of wounds that are costing us this public health issue. And those types of wounds correspond to the types of wounds that VAC therapy is utilized with. You can see the types of wounds that VAC is indicated with, shown here in the grayed out area. What is VAC therapy? VAC therapy, as it was invented by Drs. Lou Argenta and Mike Moorquast from Wake Forest University, consists of taking a black polyurethane foam, it's a reticulated foam, you cut it to the size of the wound and you put it in the wound. Kind of as you've seen the graphic here. You cover it with an adhesive-backed polyurethane drape, cut a hole in that construct, and then connect it to a therapy unit. You can see, like I said, there's a graphic of it as well as what a kit looks like in real life. Now, as you can see in the video here, if you could please play the video, as the therapy unit is turned on, that wound volume is evacuated. Let's go back. If you could please run the video. So you can see as that therapy unit's getting turned on, that wound's getting evacuated, that foam's buckling, and those tissue edges are coming together. We refer to that as MacroStrain. So in the early days, we knew a mechanical event was occurring, that tissue was occurring when we applied the negative pressure. We also knew that the wound was granulating in, was filling in. So wounds are left in this state at minus 125 millimeters of mercury, and they're left this way for 2 to 3 days while the tissue's growing in. Clinician comes in at their discretion at 2 to 3 days and changes out that wound dressing. So over the course of several days, granulation tissue occurs and it fills in the wound. So like I said, early days, we knew that we turned on the device and we knew that you got granulation tissue. We didn't really understand what was happening between those two events. The areas of orthopedics and dentistry have a concept of Meccano transduction. So you can put a mechanical force into the body responds. And we thought that was a really good concept based on what we were seeing when we started really investigating this in the late 1990s and early 2000s, to try to give us a framework to understand what was happening in the body. So I've got a device, I'm doing something with the device, I get a mechanical effect. That mechanical effect is causing a biological manifestation, and that manifestation is getting rolled up to give me a clinical outcome. So we use that as our framework to put forth all kinds of hypotheses about how this might work, because it works with a variety of different types of etiologies of wounds. Put that all on the board, tried to bucket them, categorize what all our hypotheses came to, and we came up with focused areas of study. So those are the petals that you see in the graphic on the far right side. Prioritized them and then went about systematically and exhaustively trying to understand how this therapy works. Foam tissue interactions is one of the very first places that we started out with. So we invented a 3D tissue culture model that allowed us to apply vac therapy in tissue culture. So we created a provisional matrix that had fibroblasts grown in it. We could put a manifolding material over top of it and then apply vac therapy to it, feeding it all from below in a 6-well plate. For those of you who don't know the size of a 6-well plate, each one of these plates is about the size of a quarter. So in the far left, what you see is a plate that's just kitted up, ready to go to run the experiment. Some of our early experiments, you see the results in this middle panel. In this middle panel. The cells at the top are those that are not receiving negative pressure. They look like normal cells in tissue culture. They're dendritic, they're kind of thin. When we used a manifold material made out of gauze, cells look very similar. However, when we used granufoam, which is the black foam that I talked about earlier, you saw that these cells looked quite different. The green, which stains the cytoplasms were much larger. The blue DAPI stain, which stains the nucleus, again, the nuclei were a lot larger. These are indicators of a lot of metabolic activity going on. So as we started to understand, started to examine what's going on in this wound healing process. When you think about wound healing, things that have to happen for a wound to heal. Cells have to proliferate. You got to get other cells into the environment to help build extracellular matrix. So one of the first things we wanted to make sure was, are we killing any of the cells? Is there any apoptosis going on when we're manifolding through these various different types of materials? And we saw that when we're looking with negative pressure through granufoam, we didn't see nearly as much apoptosis as we did when we were manifolding through gauze. When we looked at proliferation, we saw much more proliferation occurring in those cells that had been treated with granufoam. And then as we started to look at the ability to engender cellular migration from naive cells, we saw that the milieu that was being created by those cells that had been treated with vac therapy was much more capable of soliciting migration of naive cells than was the milieu being treated by the other treatment groups. So when we looked at this in aggregate in the beginning, it led us to believe that part of what we're doing when we're applying vac therapy is engendering a pro-wound healing phenotype. So we're moving cells further along the wound healing pathway than some of our traditional treatments of wounds. We did a little bit more work because wound healing is an incredibly metabolic process. And so we wanted to understand what was happening with the energetics of these cells. We used a stain that basically aggregates cells within the mitochondria. The mitochondria, if you remember back from high school, these are the factories where all the energy is getting produced in the cells. And the way the stain works is it aggregates in the mitochondria, and here it lights up red. So you can clearly see from the images here that those cells that were being treated with granufoam have much higher levels of mitochondria in them. And we verified this by looking at transmission electron microscopes in terms of the number of mitochondria and the size of the mitochondria. Further, we looked at molecules that were involved in terms of the energy. So we looked at ATP versus ATP ratios, had higher ATP ratios in those cells that had been treated with the granufoam. And we also saw higher levels of production of protein that were related to wound care, PDGF being one of the ones that we showed here. We also saw that with transforming growth factor beta. So, like I said, this is one of the first set of studies we did. Like, I could talk about this all day if we had the time. But then we moved on to say, okay, how do we take this information and utilize it to explain how vac therapy works? That work that we talked about a couple of moments ago contributes just to these two panels right here on this mechanism of action, when we're talking about how vac therapy works. We also looked at perfusion. We looked at edema. We looked at a wide variety of different things going on in terms of wound healing, developed preclinical and clinical studies and data to support a graphic, which allowed us to have conversations with clinicians about how vac therapy worked. We've been able to use that information to work with clinicians to be able to treat, when we looked at the numbers in 2016, over 10 million wounds. And that information is great. 10 million wounds is a lot of wounds. But when you start looking at wounds and the prognosis for people who have wounds relative to those who have cancer, 5-year mortality for people with wounds, like neuropathic ulcers or ischemic ulcers, is very similar to some 5-year cancers that are out there. Not a lot of people know that. So in terms of, again, next big thing, something to think about. We wanted to take it to the next step. We've learned a lot about how negative pressure works on open tissue. So what if we could get to the point where you can use negative pressure in wounds that were still closed tissue? You know, you had an incision, which was a wound, but it had already been sealed shut, and you didn't have the issue of it being open and trying to get it closed where you could protect the entire body from having a path for bacteria to get in. And so we've taken that information and we've worked to utilize that information to develop technologies to address incisions that have been closed but require some type of pro-wound healing progression. And Deepak's going to talk to you about that.
Thank you. So we move from the treatment of wounds to possibly preventing wounds. So how many of you know or have know of people, friends, family who've had surgery, or yourselves? Right. It turns out 8 million people who undergo surgeries are at risk for surgical site infections. And they can be devastating. From a macro standpoint, when you take healthcare-associated infections, it accounts for, SSIs account for about 22% of the cost. If you take the top 5 healthcare-acquired infections, it's about 1/3, about $3.2 billion, based on data that was published perhaps 8-9 years ago. So it's a decade old. And it's probably much worse. Now, from a personal standpoint or an individualistic standpoint, an average SSI adds up to 10 days of extra hospital time. And that translates into tens of thousands of dollars. And now what's happening is, with the change in reimbursement, hospital facilities, as many of you know, now have to absorb that cost. So there's a huge impact, not only for the patient in terms of the morbidity, the pain, possibly death, but also cost to the economy. So what could we do? And this is an example of how we, as people in industry, in research, work with external folks, clinicians. And what happened was, earlier on, we said, what about using negative pressure topically on incisions, especially in those patients who are at risk? So on average, if you're young, if you're healthy, incisions heal, and they heal pretty well. But as we get older, as we get obese, as we get diabetic, things change. So the thought was, we were developing, understanding what could happen with topical applications, and in parallel, there were other clinicians in the field who were using off-label applications of vac therapy that Chris described. They used gauze, they used gauze, or they used foam, they used interfacial skin-friendly layers and applied negative pressure. And the original thought process for a lot of them was, hey, we are sucking on wounds, right? We're just sucking out. You know, if it's not closed properly, if they're leaky, let's look at the duration of drainage. And so we kind of got more information, and we developed this dressing, and it'll give us a little bit of context as to what I'm talking about down the road, is we said, okay, let's make it convenient for these folks. So you have this foam-based dressing that has an interfacial layer, and which can come either pre-draped or not, depending on the complexity of that incision line, and then it's attached to a disposable negative pressure pump, a vacuum pump. The interesting thing is, if you have a closed incision, negative pressure really doesn't communicate necessarily directly into that incisional space. So there's this other element at play, where you have a change in the shape of the dressing as a result of the negative pressure that's been applied, and that brings in the tissues to which it's attached in a better fashion. And this is an example of a bench study that we had done to show that. So what we did was we had a proxy for tissue, and this is an incisional space which was sealed off with a film, and then you applied the dressing on the other side, and so we're looking at it from the bottom up. Another thing we looked at, and this was where it was counterintuitive to us to a certain extent. So we developed a hematoma seroma model in pigs, and what we did was we undermined areas in the belly of the animal, and so we created pockets which had incisions on top, and then we either applied negative pressure or we applied a standard control dressing. And what we did was 4 days later, we went in and scooped out the contents of that pocket. And what we found, much to our surprise, was that there was a 63% decrease in the construct that was in there. And this was completely unexpected. I mean, this was a big difference. And a more interesting thing was that there was absolutely no fluid collected in the negative pressure canister. Because the original thought was, oh, hey, we're sucking on it, there's probably compression going on, and we're just kind of minimizing that dead space. But in our pilot studies, we had seen we could effect the same sort of results if we used drainage tubes in a manner that was consistent and very appropriately monitored, but it pulled out about 100 cc's of fluid. So with our system, that fluid was nowhere to be seen outside the body. So we said, what could that possibly be due to? And we said, what are the endogenous mechanisms? And we know that the lymphatic system typically is the internal clearance highway, pathway, in addition to our blood vascular system. So what we did was we had also injected tagged nanospheres into these pockets that I mentioned. And the thought was, if these nanospheres get carried away into the lymphatics, and if we choose the right size nanospheres, they should be sequestered better in the lymph nodes. So we pre-identified lymph nodes that were harvested about the same time, and we showed about a 50% increase in this. So this is the first time we had some data to suggest that there was better involvement of the lymphatic system. And all these studies were part of a bigger umbrella program where we're looking at what happens when you apply the therapy. We apply the dressing, start therapy. We essentially establish that, there is a biomechanical change. As Chris mentioned, in the end, this is a physical cue that elicits a biological response. And there are two elements to this. As we talked about, suction, change of shape of the dressing, but it is also a much simpler, non-specific characteristic, which is the fact that you have a drape. You're keeping the bugs out. And this allows for compliance. You don't have to change dressing every so many hours. These dressings are on for up to a week at a time. And so that was one part of it. The second part of it, we also looked, as I showed you, the impact over the course of the duration of the therapy. In that previous study, it was 4 days. And we showed that there may be some involvement of the lymphatics, and this may play a role in fluid management. There have been other studies. We have things called investigator-initiated studies. So you as an investigator can come to us, and you can do studies if it's in alignment with our overall goals. And this was a study out of California, which shows, this is in a pig model again. You see control versus this negative pressure treated system. So in other words, it seems to kind of get to a further point in the healing process a little bit more quickly. So using that as a cue, we looked at longer term impacts. So we applied dressing on day 0 post-surgery, and we looked at what happened, applied the dressing and therapy for 5 days, and then determined what the quality of that incision line was 40 days after the fact. And what we showed was that the strain energy density, a measure of toughness of that incision line, which is important from a clinical standpoint if you have an open heart procedure. If post such a surgery, typically if you cough or sneeze, that's an impact load. So if you can make that incision line tougher, that's a good thing. So it did better than control, not quite as good as naive, but if you look at peak stress levels, peak strain levels, they were not statistically different. I haven't shown you that data. And what we showed also was that the healing, the incisional area, the healed part, was narrower. And we've also done gene expression analysis, which shows that the negative pressure treated specimens were further along the healing cascade. They had exited the inflammatory phase while the controls were probably still in that phase based on that data. So what does this all mean? That is all animal data, bench data. The proof of the pudding is in the clinical data. And we've been having a huge number of papers that have been coming out over the last so many years. And as a result, people have been also doing systematic analyses. And what we see here is that, this was published last year by Dr. Devinder Singh, that there's a statistically significant and consistent basis for why you might want to consider the use of negative pressure. There have been the strongest data sets come from the vascular surgery world and the arthroplasty, the hip and knee replacement world, where they've shown that high-risk patients, when using negative pressure, are downshifted into the low-risk population. So that's a pretty big impact. And also, as a result of the new data, when we first launched this system, we had a very insipid indication statement from the FDA. Use it when you have closed incisions, and effectively you'll be managing the fluids a little bit better, right? I mean, that was the implication. But the upgraded indication for use, which came out a few months ago, speaks to the fact that, let me see if this, it reduces the incidence, may aid in the reduction of incidence of seroma, and in patients at high risk for post-operative infections. So what this means is FDA is satisfied that there's some level of evidence, at least for these types of incisions, and there are more data coming. Of course, the focus thus far has been on infection. But there's more that's going on. This was a paper by Pauser et al., where they showed this was a hemiarthroplasty where a portion of the joint was replaced, and this is an incision line in the hip, and you can see Pravina being used out here. But you see clearly there's a change in coloration. This is ecchymosis, or bruising-like manifestation, but where that negative pressure was applied, you see there's this absence of color, or loss of color. And we think that is, can I go back to, please? Yeah. Is because of this phenomenon here. If you asked a lot of people a few years back, including at KCI, they would tell you that as the foam buckled, the tissue directly beneath the dressing would be under pressure, under compression. I think that's been changing quite a bit. But even now, there are whole groups of clinicians who still think there's this compression that's going on. And what we showed in this animal model, and this is an expert CT cross-section, this is dressing in place. It's the same study that I was telling you about. This is on skin. There's an incision line right there. The dressing's on. There's an endotracheal tube for reference. This is without negative pressure. When you apply negative pressure, you can see the floor there, so to speak, come up. So there's a distension of the tissues directly beneath it. And this can explain a lot of the phenomenon that were put in a black box many years ago. Why do we use -125? Because we've got blood flow. But people originally thought it had to do with fluid evacuation. That may be part of it, but there may be a physical distension of the tissues as well. It also potentially explains our lymphatic results and, of course, the Pauser results as well. And what this has done is, this has taken us to the next level of play, beyond surgical site infections. What about managing soft tissue? So if you have a knee procedure, it's not just the incision, but it's also the area around it which gets manipulated. Or if it's a breast reconstruction situation. So we've got tissue-specific or anatomy-specific dressings that have come out, and these were launched in the last 6 months. And they're doing really well. We need more data, and if your teams are interested in doing research, please contact us. This is an opportunity for collaboration. There is a need for more research. Worldwide, we have millions of new wounds. And the challenge is, it affects us at a very personal level. It affects us, our friends, our family, our superheroes. You might know Christopher Reeve, who played Superman, was paralyzed, died of complications from a pressure ulcer. The irony is, oftentimes, these wounds are treated or are considered not to be disease in itself, but as a comorbidity. So they don't get the same level of attention from the funding agencies. So if you look at the National Institute of Arthritis and Musculoskeletal Diseases and Skin Diseases, leprosy, which has 100 new patients a year, gets 15 times more funding than pressure ulcer research, which has 2.5 million new patients a year. Of course, to take this passion to action, as one of the speakers this morning mentioned, it takes more than a team. It's truly a village, an ecosystem, maybe universes, right? So we have a huge number of people at KCI, be it through research and development and engineering, the quality folks, the health economics and regulatory individuals, the sales people, marketing people, are all needed to take these ideas, make them something that's usable and doable and can be gotten into the hands of our patients. Because in the end, that's exactly what matters. So with that, I'll be happy to answer any questions, as will Chris.
Great talk, Max Mamonk in Baylor College of Medicine. So by applying the negative pressure on your wound, you're creating a hypoxic condition. So there's less oxygen present in there, right? And that resembles cancer, which also kind of a wound healing process. There's a lot of tissue remodeling. And so hypoxia in cancer does two things. First is it kind of switches metabolism from oxidative phosphorylation into glycolysis, which provides the necessary blocks for growth. It's not very energy efficient, but provides the building blocks, which is exactly what you need in wound healing response to. And also it promotes vascularization. So do you think by creating a hypoxic environment and just depriving this region from oxygen, this mechanism can contribute to what you're seeing in those patients?
So we're not preferentially removing oxygen from the wound area.
No,
We're
I mean,
basically-
you are making the atmosphere less saturated, but there's less.
Well, the partial pressure of
right.
oxygen, we're not enriching the area with nitrogen. I mean, the ratio of oxygen to nitrogen is the same in the wound volume.
Sure.
So.
But the absolute concentration of oxygen atoms is lower just because the pressure is lower.
No, the relative concentration is the same.
No, relative is the same, but
He's talking about the absolute.
As you drop the pressure, the number of molecules per
Yes, there are. Yes,
cubic
there's fewer
millimeter
molecules
is long.
because there's
Exactly.
fewer molecules in there because
So
you're
you're-
removing the.
Right, so you have less oxygen in there
Right.
in general. So do you think this may contribute to it?
We have done work looking at HIF and at various inducible factors that are related to hypoxia. And, the results haven't been quite as profound in terms of looking at the expression with those molecules historically. To be honest, we haven't looked at it when we first did that work. That was about 18 years ago. So where technology is involved in the ability to look at things in greater depth is probably something that we could redo. But in terms of what we saw in our original work, we really didn't see that the changes were being stimulated by hypoxia per se.
Because you can easily check that by recreating an inert atmosphere with inert gas or nitrogen itself, by reducing the presence of oxygen, see if it will at least reconstitute some of these effects.
Yeah, that's a great suggestion.
Yeah.
Hi, nice work. Kristine from Texas Biomed in San Antonio. I have a question for Chris regarding the foam. Is there anything special about the foam that would preclude it from being replaced by something more biocompatible? It sounded like after 2 days you replace it, so I would imagine there's some cell infiltration that you lose when you take it out and replace it with something else, something more biocompatible, maybe decellularized tissue or some kind of biocompatible polymer might be a better alternative.
So our early work suggested the porosity of the foam had an impact because of the strain profiles that you're creating with the interaction. Like, if my fingers are the struts of the foam and my hand is the tissue, and so when you evacuate it, you've got basically a strain profile occurring at that tissue interface. So the extent of strain that we were producing appeared to have an effect. We have done work with biocompatible materials because, exactly as you've seen, what's happening is we're generating so much tissue within the 2 to 3 day time frame that the tissue is basically getting incorporated into the foam, and then when you're doing the dressing change, you're causing a lot more trauma. And obviously you don't want to incorporate a non-biocompatible material into the wound. We've done a lot of work with biocompatible materials, and a couple of different things come into play. One, the issue of all wounds are colonized. So there's the possibility of having a sinusitis or infection because you have an inert material in there and you're planning on keeping it in there for the duration, right? So that's one thing. Two, the biomechanics of it, the mechanical profiles change once the tissue starts growing into that foam and you're not stimulating the type of MacroStrain that you were by refreshing that interface. So does the foam seem to do something special? Yes, it appears to be. The question is it the amount of MacroStrain that's being engendered? Could you maybe modify that by doing something different with respect to the mechanics and how much tissue you engage and how that tissue is engaged? That is definitely something that's a possibility for, let's be honest, that's the kind of stuff that we're studying.
Thank you.
Thank you.
Thank you so much.